He was the best mechanic in Europe, and in one silent moment he understood that his skill was worthless. In a captured ordnance depot in Normandy, in the summer of 1944, a German mechanic bent over the engine deck of a knocked-out American Sherman. He had spent his whole life learning to make things fit. He carried a caliper. He carried a file. He knew, the way a surgeon knows a body, that a replacement part never simply seated itself. It had to be coaxed, measured, dressed, and persuaded into place by a man who understood it. That was his craft. That was his pride. He lifted the ruined engine out of the tank. Then someone handed him a fresh one, straight from a wooden crate, stamped in a language he could not read. Built 4,000 miles away in a city called Detroit. He set it into the empty bay, expecting the long fight of steel against steel. There was no fight. The bolt holes lined up, the shafts aligned, the whole thing dropped in as if it had always belonged there. And in that silent moment, without a single word spoken, the best mechanic in Europe understood that he had already lost the war. Why did that part not need him? The answer begins almost a century and a half earlier. Take a moment to settle in with a warm drink. Before we start, glance at the clock and tell us the time where you are. Then relax and enjoy another remarkable story from World War II. On the 8th of November, 1942, 1 minute past midnight, workers laid the first keel plate of a new cargo ship at the Kaiser Shipyard No. 2 in Richmond, California. The men worked in shifts that never stopped. Welders crawled along the seams while cranes lowered whole prefabricated walls of steel into place. Sections that had been built in factories far inland and carried to the coast by rail. 4 days, 15 hours, and 29 minutes after that first plate touched the blocks, the finished hull slid down the ways and into San Francisco Bay. They named her the SS Robert E. Peary. A week after her keel was laid, she was handed over to the Merchant Marine, fully fitted, ready to carry cargo into a war zone. The American newspapers called it a stunt. Henry Kaiser called it an incentive ship, a demonstration of what his methods could do. When a nation decided to be in a hurry, but there were other men reading about her far away in the wire reports that filtered into Hamburg and Bremen and Danzig, German engineers studied those numbers at their desks. They did not call it a stunt. They understood exactly what they were looking at. They called it a method they would one day have to copy. What they did not yet understand was that copying it would help destroy them. To see why, you have to leave the shipyard and walk into a German machine shop, any one of thousands scattered across the Reich. Picture the light coming gray through high, dirty windows. Smell the cutting oil and the hot iron shavings curling off the tools. Hear the low patient turning of belts and gears. There, at a lathe worn smooth by decades of hand, stood a figure the Germans held in deep respect. They called him the Facharbeiter, the skilled craftsman. He was the soul of German industry. He had served a long apprenticeship, years of it, sweeping floors before he was ever allowed to touch a machine. He could read a drawing, the way a musician reads a score. When a part came off his machine, he finished it himself, with a micrometer and a file, shaving away metal a hair at a time until it was perfect. He would hold the piece up to the light, turn it slowly, feel the edge with his thumb. If two pieces did not quite meet, he made them meet. He took pride in the making. He was, without exaggeration, among the finest workmen the world had ever produced. And that pride, that beautiful and stubborn pride, would help lose the war he was about to fight, because on the other side of the ocean, in an American factory, the same part was not finished by a proud man with a file. It was finished by a gauge, a hardened steel block that an inspector clamped onto the piece for a single second. If the part passed, it went into a bin with 10,000 identical brothers. If it failed, it was thrown away, and the man who made it was warned. No one adjusted it. No one loved it. No one made it fit. It already fit because it had been made to fit every other part like it, anywhere in the country. That was the difference between the two worlds. And that difference had taken almost 150 years to build. The story of how America learned this begins in 1798 with a Connecticut inventor named Eli Whitney. He signed a contract with the War Department to deliver 10,000 muskets, and he made a startling promise. The parts of those muskets, he said, would be interchangeable. A lock taken from one weapon would fit any other weapon, with no filing, no hand fitting at all. In January of 1801, he gave a famous demonstration. He stood before President John Adams and Vice President Thomas Jefferson, laid out the pieces of 10 muskets on a table, and invited Jefferson to assemble a working firearm from parts chosen at random. Jefferson did. It worked. The audience was amazed. It was also a lie. The historian Merritt Roe Smith, digging through the records more than a century later, showed that Whitney had rigged the whole performance. He had taken those parts back in his own workshop and hand-fitted them in advance, then marked them so they would go together for the show. He had duped the government of the United States. The dream of interchangeable parts was real, but in 1798, it was still only a dream, and the man who promised it could not actually deliver it. The real breakthrough did not come from a showman. It came slowly, painfully, from the government armories at Springfield in Massachusetts and Harper's Ferry in Virginia. At Harper's Ferry, a gunsmith named John H. Hall worked under contract to the Ordnance Department, and he spent 20 years chasing the thing. Whitney had only pretended to have 20 years of building jigs and fixtures to hold each part in exactly the same position, 20 years of designing special milling machines, 20 years of grinding hardened steel gauges so precise that an inspector could judge a finished piece in the time it took to blink. 20 years of throwing away everything that did not pass and dropping any supplier who sent too many rejects. By 1819, Hall had done it. His breech-loading rifle, in the judgment of the historian David Hounshell, was the first product ever made in large numbers whose parts could be freely exchanged with one another and still work. Not a demonstration, not a fraud, a real thing, made by the hundreds whose pieces were truly interchangeable. Think of what that patience cost. Think of the thousands of finished parts swept into the scrap bin because a gauge said they were wrong by the width of a hair. Think of the suppliers turned away, the arguments, the slow grinding years with nothing to show but rejected metal. Hall did not build a better rifle. He built a way of building a discipline, a habit of mind that put the standard above the man. It had taken 2 decades of patience to reach that single point, and America would spend the next century building an entire industrial civilization on top of it. The world noticed in 1851, the British held their great exhibition at the Crystal Palace in London, a showcase of the finest manufacturing on earth. Among the exhibits were revolvers from Samuel Colt of Hartford and rifles from a small firm in Windsor, Vermont. British engineers examined them and were stunned. These American weapons were not the handmade masterpieces of a proud craftsman. They were something new, something made by machines to a standard made to be identical. The British coined a name for what they were seeing. They called it the American System of Manufactures. And then the British did something revealing. They formed a committee, sent it across the Atlantic to Springfield in 1853, and placed orders for American machine tools to re-equip their own Royal Small Arms factory at Enfield. The technology that had been born in Connecticut and matured in the hills of Harper's Ferry now crossed back over the ocean to Europe. It was there for anyone to take. The blueprint for the future was sitting in plain sight, but Europe never fully embraced it. And German industry, above all, kept faith with its old culture. The machines could be bought, the methods could be studied, yet at the heart of every German workshop, the Facharbeiter remained. He kept his file, he kept his caliper, he kept his pride in making each part fit by hand. A German lathe in 1905 still produced work finished by a man, not a gauge. To the German mind, this was not backwardness. It was excellence. It was the very thing that made German engineering the envy of the world. Daimler and Benz, Krupp and Zeiss, Bosch and Maybach. These were names that meant precision, meant quality, meant the finest work a human hand could achieve. And that was exactly the trap. Because the Facharbeiter made things fit one at a time. He was a genius of the single object. But a modern war would not be fought with single objects. It would be fought with rivers of identical steel, with tens of thousands of engines and tanks and hulls that had to be repaired and replaced faster than they could be destroyed. In that war, the question would not be who could build the most beautiful part. The question would be whether a broken part could be pulled out and a fresh one dropped in by a tired man in a muddy field, with no time and no file. America had been answering that question for 150 years. Germany had never really asked it. In May of 1940, the two philosophies were about to collide. German tanks poured into France, and within 6 weeks the French army had surrendered and the British were fleeing across the beaches of Dunkirk. In the Oval Office in Washington, President Franklin Roosevelt understood that his country might soon be dragged into the same fire. He asked one plain question of the men around him: who in this country could actually build the weapons America was going to need? The financier Bernard Baruch answered him in 3 words, and then repeated the same 3 words twice more. To be certain, the president heard, first, Bill Knudsen; second, Bill Knudsen; third, Bill Knudsen, the German mechanic in that Normandy depot, 4 years in the future, holding an engine that had dropped into place without a fight, would never hear the name Knudsen. He would never know that the reason his file was useless had been decided in a Washington office before the United States had even entered the war. He only knew the feeling in his hands as the steel settled home. Somewhere across the ocean, a nation had learned to build a part that did not need him, and now that nation was coming. William Knudsen was a Danish immigrant who had walked off a boat in New York Harbor in 1900, 20 years old and nearly penniless. He had risen through the Ford Motor Company under Henry Ford himself, organizing the moving assembly lines at Highland Park that poured out the Model T by the millions. He had crossed to General Motors and climbed all the way to its presidency. He understood industrial production at a depth almost no other living man could match. When Roosevelt offered him the job of running America's war production, Knudsen gave up a salary north of $300,000 a year and accepted a federal wage of $1. He did it because he believed his adopted country was about to need everything he knew. Knudsen had créé, and he repeated it to anyone who would listen. Speed produces nothing in manufacturing. He said, accuracy is the only straight line to greater production. At the plants he had run, he was famous, almost feared, for confiscating hammers and files off the factory floor. If a part did not pass the gauge, it did not get tapped into place or dressed with a file, it was thrown out, and the supplier who sent it was put on notice. To a proud German craftsman, this would have looked like madness, throwing away good metal that a skilled hand could easily correct. To Knudsen, it was the whole secret. A part you had to correct was a part that would fail somewhere else. In another plant, in another tank, in a field under fire where no craftsman waited. The only part worth keeping was the one that needed no correction at all. Starting in 1940, Knudsen drove that principle into every contract and every supplier in the United States that wanted to build weapons. And he needed tanks. In 1940, the United States Army owned fewer than 400 tanks, nearly all of them obsolete. He went looking for someone who could build modern medium tanks in real numbers. And he found K.T. Keller, the president of Chrysler. Keller agreed. Knudsen called in Albert Kahn, the architect who had designed Ford's great plants, and Kahn drew up a factory on a stretch of Michigan farmland outside Detroit. Ground was broken in September of 1940. The first tank rolled off the line the following April, before the roof was even finished. They called it the Detroit Tank Arsenal. It ran 5 city blocks long and 2 city blocks wide. It held 1,000 machine tools and 8,000 specialized jigs, each one built to hold a part in exactly the same place every time, forever. That single arsenal, run by Chrysler, would build tens of thousands of tanks and hand back tens of millions of dollars to the Treasury for coming in under cost. And it was not alone across the country. 10 other factories joined in building the same tank. A General Motors arsenal in Michigan, a press steel plant in Illinois, a railroad car builder in Pennsylvania, locomotive works in New York and Ohio and Philadelphia, a car and foundry company on the far side of the continent, in Washington State. 11 plants in all, scattered 3,000 miles apart. Some of them run by companies that had never built a weapon in their lives. By the time the war ended, together they had produced almost 50,000 Sherman medium tanks. The exact figure from the standard reference by the historian R. P. Honeycutt is 49,234. Here is the part that mattered, the part that no other nation on earth could match: a tank built at the arsenal outside Detroit and a tank built 3,000 miles away. On the Pacific coast, used parts that interchanged, the bolt patterns matched, the mounting brackets fit, the shaft splines aligned, the transmission unbolted and slid out as a single unit, and a fresh one slid back in. And the engine bay, the very heart of the machine, would accept any of 4 entirely different engines, designed and built by 4 entirely different companies, 4 engines, 4 firms, 1 tank. That had never been done before in the history of warfare. The first engine was the Continental Radial, a 9-cylinder air-cooled engine that had begun life as an aircraft power plant back in the 1920s. It produced around 400 horsepower. The men who built it added a fan and a shroud to move the cooling air that a propeller would once have supplied, and dropped it into the early Sherman variants. Continental built tens of thousands of them, far more for tanks than had ever been built for airplanes. The second engine was a General Motors twin diesel, a strange and clever thing. It was a pair of ordinary bus and truck diesel engines yoked to a common output shaft, each one keeping its own crankshaft, so that if one failed, the other could still drag the tank home. The Marine Corps loved it because diesel fuel did not catch fire as readily as gasoline when a tank was hit, and a tank that did not burn gave its crew a few more seconds to live. Thousands went to the Red Army through Lend-Lease as well. A Soviet after-action report from a Guards Tank Brigade, dated the autumn of 1943, noted that, compared to their own 34, the American tank was easier to control and more durable on long marches because its engines did not need constant adjustment. That last phrase carried the whole argument inside it. The engines did not need constant adjustment. That was the American gift, written in a Soviet officer's report without his even knowing what he was describing. The third engine is the one that, more than any other, showed what American industry could truly do, in 1942, the Army needed more tank engines than the existing suppliers could build. Chrysler was asked to design one, and fast, there was no time to draw a new power plant from a blank sheet. So two Chrysler engineers did something that sounds like a joke and turned out to be a marvel. They took 5 ordinary 6-cylinder car engines, the same engines that powered Plymouth sedans off the showroom floor, and they clustered all 5 around a single central crankcase, driving one common output shaft through a set of gears. 5 car engines, 30 cylinders, 5 carburetors, bolted together into one tank engine. It should have been a nightmare of complexity. Instead, it became the most reliable engine in the entire Sherman family. Test data from the Army's proving ground at Aberdeen in 1944 showed that crews running the 5 engine clusters spent only around 45 hours on engine maintenance during the trial. The figures for the other engines ran to more than 100 hours, and in some cases over 140. The strangest, most improvised engine of them all was the one that broke down the least. British crews, who used this version as the basis for their upgunned Sherman Firefly, the one Allied tank in the West whose gun could reliably punch through the front of a Tiger or a Panther, reported thousands of miles between major overhauls, a cluster of 5 sedan engines, thrown together in a hurry, outlasted them all. That was not luck. That was a system so deep that even its rush jobs came out dependable. The 4th engine had the strangest origin of all. Before the war, Ford had designed a large aircraft engine, a beautiful all-aluminum 12-cylinder power plant. Hoping to win a contract from the Army Air Corps, the contract never came. The Air Corps had chosen another engine, and Ford was left with a finished design and nowhere to put it. When the Ordnance Department asked whether it could be turned into a tank engine, Ford's engineers simply cut 4 cylinders off the design, keeping the aluminum block, the overhead camshafts, the whole sophisticated architecture. The result was a 500 horsepower aluminum Vate with the engineering pedigree of a racing engine, and Ford built it to be driven through mud and snow inside a Sherman. It powered some of the best Shermans of the war, and eventually the heavy tanks that followed them. 4 completely different engines, 3 different engine companies, and whichever one was pulled, whichever Sherman it was bolted into, it fit. The bell housing matched the transmission, the mounting brackets matched the rails, the cooling shrouds bolted up, the hoses connected, the wiring plugged in, the part dropped right in. In the orchards and sunken lanes of Normandy in the summer of 1944, an American tanker described what that meant in words recorded in Hunnicutt's history. Changing an engine, he said, was an easy matter. It took little more than 4 hours, and it beat all hollow. He added, the best time the Germans could manage. He did not say it with pride. He said it the way a man states, a simple fact of his working day, now crossed to the other side. By the autumn of 1942, the German army had a problem it could not solve with craftsmanship. Since the summer of 1941, they had been fighting the Soviet 34, a tank with thicker armor, a bigger gun, and wider tracks than anything the Germans had in service. Their existing tanks were outclassed. Hitler ordered a new medium tank to beat the 34, and 2 firms competed for the contract. The company known as MAN submitted one design. Daimler-Benz submitted another. Hitler personally preferred the Daimler-Benz design, partly because it looked like the 34 that had frightened his generals, but the Army Ordnance Office chose the MAN design instead, because the big new turret with its long gun would only fit on the MAN hull. The tank they chose was the Panther. On paper, the Panther was magnificent. Its long gun was perhaps the most accurate tank gun of the entire war. Its sloped frontal armor was effectively impenetrable to almost every Allied tank gun in service. A Panther could kill a Sherman at 2,000 yards, while a Sherman firing back at the Panther's front plate could rarely penetrate at any range at all. In a straight duel, on a firing range, the Panther was the superior machine, and every honest Allied tanker knew it. But man alone could not build a Panther in the numbers the Army demanded. The plan called for 600 a month, so the design was licensed out to 3 more plants, including Daimler-Benz, the very firm that had lost the competition, now ordered to retool and build its rival's tank from MAN's drawings. Fourplan, building the same tank. On paper, this was exactly what the Americans were doing with the Sherman at 11 plants. It should have worked. It did not. And the reason it did not is the whole heart of this story. To manage the parts, the German Ordnance Office assigned every Panther component its own drawing number. The historian Thomas Jens, whose technical study of the Panther written with Hilary Doyle is the definitive work on the tank, explained why each drawing number identified the exact part belonging to each version of the Panther, and here the engineering disaster hides inside a single quiet sentence. The reason every part needed its own drawing number was that the same nominal part, a drive sprocket, let us say, was actually several different physical parts, depending on which plant had built it and when. A drive sprocket built by man in the autumn of 1943 was not dimensionally identical to a drive sprocket built by Daimler-Benz in that same autumn. They looked the same, they did the same job, but a mechanic in a recovery yard could not simply pull one and bolt on the other. He had to check the chassis number, verify the drawing number, and fit the part by hand if it would fit at all. Jensen Doyle documented these variations across nearly every part of the Panther. The drive sprockets differed between plants. The commander's cupola changed from one type to another at different points at each of the 3 factories. The side skirts used different mounting brackets at one plant than at another. The exhaust shrouds varied. The turret drives varied. The hull machine gun mounts varied. In an interview, Jens once summarized the whole German mindset in a single remark about the way these factories work. The assembly workers, he said, would build a vehicle with whatever was on hand and whatever was easiest to reach. That was the Facharbeiter again, the proud craftsman, standing at the center of the assembly hall with his caliper and his file. If the part did not quite fit, he made it fit. He was a professional. He was proud. He was among the best in the world at what he did, and he was the exact reason an American ordnance crew could swap a Sherman engine in 4 hours, while a German recovery team working on a tank built in their own country could not. The engine that powered the Panther was a large water-cooled gasoline V12 built by Maybach, one of the proudest names in German engineering. But it had been designed in a hurry, enlarged from a smaller engine to squeeze out more power, and in the enlarging, the engineers had kept the cylinders spaced as before. That left the walls of metal between the combustion chambers dangerously thin. Head gaskets burned through, not at the edges where a mechanic would expect it, but between the cylinders themselves, where the metal was starved. The result was catastrophic. And it was not the only fault. Fuel lines in the engine bay leaked, carburetors overflowed and soaked the compartment with raw gasoline. A single spark from the magneto or a touch of the hot exhaust turned the whole engine bay into a fireball. Panthers caught fire on their approach marches, on the road. Before they had fired a single shot at the enemy, the engineers at Maybach kept trying. They added sealing rings to the cylinder heads, a fix personally suggested by Ferdinand Porsche. They strengthened the fuel pump. Late in 1943, they locked the engine governor to a lower speed, which dropped the rated power and slowed the tank, all to keep the engines from tearing themselves apart. A British interrogation of a captured Panther crewman in the summer of 1944 recorded that his battalion had been averaging only around 450 miles between engine failures, but even that was not the worst part. The worst part was a single gear. The final drive was the gearbox that took the engine's power after the transmission and delivered it to the tracks. The Panther used a simple spur gear system there, and Thomas Jens, in his study of the tank, called the final drive, the weakest part of the whole Panther. It was a risky choice. Jens wrote to use that kind of gear for transferring the drive power, especially given that the steel available to Germany during the war did not have a particularly high tolerance for stress. And behind that weakness stood a decision made at the very top, Albert Speer, Hitler's own armaments minister, admitted it plainly in his post-war memoir. The Panther had been designed as a 30-ton tank, but over the course of its design, Hitler kept insisting on more armor and bigger guns, until the tank had swollen to 48 ton, the original weight of the much heavier Tiger. The final drive had been engineered for a 30-ton machine. It was now being asked to drive a 48-ton one through that same single fragile gear. The gears sheared. Jens documented that in 1 month of normal operation, one unit had to replace 13 final drives across 30 Panthers, nearly half of them in a single month with no enemy involved. After the war, French Army engineers who tested captured Panthers reached a brutal conclusion. The truly weak spot of the Panther, they found, was its final drive, which had an average fatigue life of only around 150 kilometers, a little over 90 miles. 90 miles, that was the distance a Panther could be expected to travel before the gears in its final drive tore themselves apart. An American Sherman, by contrast, was expected to run for thousands of miles between overhauls. The German tank could outshoot the American tank at any range. It simply could not reliably drive to the battle, and the steel that should have made those gears strong was running out. A report from the Watertown Arsenal in early 1945 recorded the steady collapse of German armor steel. Before the end of 1943, German armor plate contained a healthy share of molybdenum, the alloying element that gives steel its toughness. By 1944, that share had fallen by half. The most recently examined plates, the report noted, contained no molybdenum at all. The reason was simple. The mines were being overrun and cut off ohne be ohne. As the Reich shrunk by the last months of the war, Panther front plates, once the most invulnerable armor of any tank in the world, had grown brittle when a heavy Soviet shell struck one and failed to punch through. The plate itself would often crack from the blow, and large fragments would break off the inside and fly through the crew compartment, killing the very men the armor was built to protect. The beautiful tank was being poisoned by the collapse of the nation building it. All of this came together at one of the largest battles in human history. In the summer of 1943, the Germans launched a great offensive against the Soviet salient at Kursk, and the Panther was to make its combat debut there. Around 200 of them were issued to a single tank regiment. The Inspector General of the Panzer Troops, General Heinz Guderian, had spent weeks trying to talk Hitler out of the whole attack. He believed the Panther was not ready, that the armored force was being thrown away for nothing. At a meeting that spring, Guderian asked Hitler directly whether he believed anyone even knew where Kursk was. Hitler answered that Guderian was quite right, and admitted that the very thought of the attack made his stomach queasy. Then he ordered it anyway. The Panthers began breaking down before they ever reached the start line. Several caught fire on the road march from the railhead. On the morning of the attack, Out of the 200 that had been issued, only a portion were still running. Within hours of the jump-off, more were lost. By the evening of the fifth day, Guderian's own report, preserved in the German Federal Archive, recorded that only about 10 Panthers were still operational at the front. 10 out of the nearly 200 that had rolled toward Kursk with such promise. Some had been knocked out by Soviet guns and mines, yes, but many had simply broken. Their engines had failed, their final drives had sheared. A captured German report summed up the disaster in one sentence. Before even reaching the first assembly area, it said, half the vehicles were out of action, 2/3 of those from engine breakdowns, and 1/3 from the transmission. And here is the cruelest truth of it. The gun was so good that even the handful of Panthers still running inflicted terrible damage on the Soviet tanks. In pure killing power, the Panther proved everything its designers had promised. But it did not matter. A tank that cannot reach the battle cannot win it. A gun that is the finest in the world is worthless, bolted into a hull that will not move. Guderian later called the failure at Kursk a decisive defeat, after which the enemy held the initiative and never gave it back. The Germans had built the better tank, and the better tank was sitting broken on the road, waiting for a craftsman with a file, while the war moved on without it. The pride went deeper than habit. It was built into the metal itself, and into a war that was already consuming the very steel the Germans needed to make their beautiful parts fit. But there was one more place. The same disease would show itself. One more time, the Reich would try to leap to mass production without the foundation beneath it. And that time, it would happen at sea. The American answer to a broken tank was not a single genius with a file. It was a system built and rehearsed long before the first shot was fired. The Army organized its repair work into 5 levels, each one deeper than the last. The tank crew themselves did the daily checks. The unit mechanics did the small repairs in the field. The division's ordnance company did the medium work in mobile shops set up under the trees. The heavy maintenance battalions at Army level swapped whole engines and transmissions and welded torn hulls back together. And behind all of them stood the great rebuild depots in England, in Italy, and all the way back in the United States. It was a factory that reached from the front line to the far side of an ocean, and every level of it depended on one thing. The parts had to fit. At the top of that system in Washington stood the Chief of Ordnance, General Levin Campbell. When he took over the whole Ordnance Department in the summer of 1942, his very first order set the tone. Whenever any member of the department of any rank ran into red tape while trying to get his job done, he was to throw the red tape out the window. Except that Campbell wrote as a definite general order, under him, the department became a $30 billion a year industry. And the miracle of it was measured not in effort, but in falling cost. The price of a Thompson submachine gun dropped from around $90 to about $20. None of that came from working men harder. It came from standardized parts made in volume that fit every time. In Normandy, Campbell's system met its first test under fire. An Ordnance Heavy Maintenance Company landed on the Omaha beachhead just days after the invasion. Part of its strength already lost when a landing ship was hit in the channel. The men who made it ashore, led by a captain named Papenburg, were working on shot-up Shermans within 48 hours of touching the sand. Papenburg later received a medal, his citation, noting that he had performed a heroic task in refitting, repairing, and keeping in operation badly needed tanks. Other units leapfrogged forward right behind the fighting divisions. The oldest ordnance company in the Army, with a lineage running back to the last war, opened the first forward repair shop within the first weeks, its men working long after dark by flashlight inside blackout tents. Recovery crews came ashore with heavy tank transporters that could drag a knocked-out Sherman off the front line and back to a collection point. There, the crews judged each wounded tank. If the hull could be saved, fresh parts came out of the crates, and the tank went back into the fight. If it could not, the good parts were stripped out for the next tank. And the rest was crushed. And then came the moment that showed what the American system truly was. In the summer of 1944, the Allied advance had bogged down in the hedgerows of Normandy, thick earthen banks that stopped tanks cold and turned every field into a fortress. A young cavalry sergeant named Curtis Cullen designed a solution, a set of steel tusks welded to the front of a Sherman that let it cut straight through the banks. It was a brilliant field improvisation, but the brilliance of the idea was not the point. The point was what happened next. An ordnance heavy shop battalion took Cullen's design and built almost 300 of the cutters in 48 hours, welding them onto 3 out of every 5 tanks in the First Army in a single week. They did it in time for the great breakout that finally ended the Normandy stalemate. 300 custom-built devices, designed by a sergeant and mass-produced by a repair battalion in 2 days. In a combat zone, that was not a workshop. That was a second factory, operating in the field, fed by an ocean pipeline that delivered identical parts that fit. The German craftsman, for all his genius, had nothing that could answer it. And while the American system proved itself on land, the German Reich made one last attempt to leap to mass production, this time under the sea, and it ended in the purest disaster of all. By 1943, the U-boat war in the Atlantic was effectively lost. Admiral Karl Donitz went to Hitler with a promise, a new generation of submarines, so advanced it would bring the whole campaign back to life. The design was called the Type 21, and on paper, like the Panther, it was a masterpiece. It carried many times the battery power of any earlier boat. It could stay submerged for days and outrun a warship underwater. If Germany could have built them in numbers, it might truly have changed the war at sea. To mass produce them, Speer hired a man named Otto Merker. And here the German mind made its most revealing choice of the entire war. Merker was not a naval architect. He had never built a submarine. He had never built any kind of ship. He was a truck builder, brought in precisely because he was a manufacturing man. Merker decided the Type 21 would not be built the old way, in a slipway from the keel up. Instead, the boat would be split into 8 prefabricated sections, each one built at a separate inland steel factory by firms that had spent their lives making girders for buildings and bridges. Around 32 different subcontractors would build sections in parallel, and the finished pieces would be shipped to 3 assembly yards and welded together. It was en face, exactly the Kaiser method that had built a cargo ship in 4 days. It was exactly what the German engineers reading those wire reports had said they would have to copy, but they had copied the shape of the thing without the substance beneath it. The chief naval architect wanted to build a single prototype first, to work the bugs out before mass production. He was overruled on grounds of schedule. No prototype was ever built. The design went straight from the drawing room into full production at 32 factories that had never built a submarine in their lives, and the disaster, when it came, was almost mathematical. The tolerances in submarine building are savagely exact, for the hull must hold against the crushing weight of the deep sea. The Type 21 sections arrived at the assembly yards with deviations of up to 3 centimeters, more than an inch of error on a pressure hull. They did not fit together. They had to be torn apart and rebuilt on the ways. The very labor the whole system was supposed to eliminate Pressure tests kept revealing lethal weld defects. The steel, altered to save scarce alloys, made the welds brittle, hulls cracked. The reason was the same reason the Panther parts did not match. There was no central authority for tolerance. No William Knudsen walking the floor and throwing out any part that failed the gauge. Each of the 32 subcontractors decided for itself what was good enough. The naval historian Clay Blair described the result plainly. The boat, he wrote, was hurriedly prefabricated in 32 factories, and the 8 major hull sections were crudely made and did not fit together properly. Now come the numbers that end the argument forever. Germany commissioned around 119 of these submarines, and of all of them, exactly one ever sailed a real war patrol. Her name was U-2511. She slipped her lines at Bergen. In Norway, on the evening, Hitler shot himself in his Berlin bunker. A few days later, with the war ending, she received the ceasefire order and returned to port. She had maneuvered into an attacking position on a British cruiser and then turned away. She had not fired a single torpedo. 119 boats built, 1 patrol, 0 torpedoes fired. The other 118 sat at their docks, not seaworthy. Their copied hull sections never having fit together. Their welds too dangerous to trust to the sea. And the cost of that failure is the final twist of the whole story. A senior German naval engineer estimated after the war that each Type 21 had swallowed steel equal to about 30 Army tanks. One historian concluded that the whole program had cost the German war effort something on the order of 5,000 tanks. At the exact moment its armies on both fronts had been ground down to skeletons, Germany had torn 5,000 tanks worth of steel out of its own hand to build submarines that could not sail. In a desperate attempt to copy a method it had never taken the century to master, that is what happened when the Reich tried to leap straight to the avalanche. It had no Springfield, it had no John Hall at Harper's Ferry, it had no long inheritance of the gauge. It tried to reach the summit in a single bound, and the fall killed it. So return at the last to that German mechanic in the captured depot in Normandy, standing over the engine bay of a dead American tank. He does not know any of these names. He has never heard of Knudsen or Hall or Cullen. He knows only what is in his hands. He has lifted out the ruined engine, and someone has handed him a fresh one from a wooden crate built 4,000 miles away, and it has dropped into place without a fight. He does not need his caliper. He does not need his file. He does not need the 3 hours of patient dressing that his whole life has taught him. He just bolts it down. And in that moment he understands the thing his entire proud culture never learned. He is looking at a part that does not need him. For 150 years, one nation had been building not a better tank, but a better part number, a discipline that put the standard above the genius of any single man. In the end, the war was not won by the finest gun or the thickest armor or the most brilliant engineer. It was won by the humble miracle of a part that simply dropped in. Germany had given the world Daimler and Krupp and Maybach, and none of it was enough. America had asked one plain question for a century and a half: would the part fit in a muddy field, in the hands of a tired man with no time to spare? And America had answered it. Germany never did.